So let's look at an example of using that truncation error theorem. So here we have an approximation, a very crude approximation. We have an infinite series, but we're just going to use the first three terms. And we want to see what would be our upper and lower bounds. Remember that theorem gives us both an upper and lower bound on your error. So the first thing you need to do is determine what partial sum is this, right? So remember, in our terminology of partial sums, this is S sub 3, right? It means you've added up the first three terms. This thing adds up to something, S. So we're interested in how far off this partial sum is from the actual sum. That's what we call the remainder. So remember, we defined R sub n, or in this case, R sub 3 is what is the difference between the actual and that approximation. So we have two integrals, right? One for the lower bound, one for the upper bound. So the lower one starts at n plus 1, right? So this is our n. So n plus 1 would be 4 to infinity. And then of the function, what was the function? The function means whatever the function is, you would integrate in the integral test. So the function version, the continuous version of that thing. So our function is not 1 over n squared, but 1 over x squared, the corresponding function. And we know that this error that we're interested in is whatever it is, it's trapped between that and the integral from n to infinity of that function as well. So you're doing the same integral twice, just with different limits. So we want to make these proper first, right? These are improper integrals. Remember, first step is to write it as a proper integral. So we're going to go from 4 to b and let b go to infinity. And then go from 3 to b and let b go to infinity. Antiderivative of 1 over x squared, that's just power rule, so it's negative 1 over x. Right? You raise that negative 2 power to a negative 1, and then divide by negative 1. So I'll be evaluating that at b, so negative 1 over b minus a minus, so plus 1 over 4. And then same thing over here, except for we're evaluating the lower limit there of 3. And then just take your limit. That's going to go to 0. That's going to go to 0. And we see that our error is no smaller than a quarter and no bigger than 1/3, which is a pretty big error, right? We're off in the first decimal place. But we only added up 3 terms of this series, so it's no surprise that we have a relatively large error. If you think about machine computation, it's no time at all to have a machine add up the first few million terms of that. So it's fairly easy to get that error down quite low quite quickly. And what I'd like to do is use Desmos so we can kind of see this in action. What would the partial sums look like? Let's see them converging to the actual sum. And so what we have here is that orange line represents the actual sum. And if you'll notice, it's actually pi squared over 6. This is actually a famous series, and the proof for it I'll give you guys a link to. You can actually prove that this thing equals pi squared over 6, which is interesting. And that green line is just showing the error. How far is the partial sum? The current partial sum is the purple dot. And because my sum there is just adding up to b, and I've got b at 1 right now. So let's go ahead and hit play and watch as that error shrinks. And actually for this, it shrinks pretty fast. You know, we're off, where are we now? We're just at about 20 terms, and that error is getting down quite small. We're now probably under, we're in the hundredths now, and we've only added up 20 or 30 terms. By the time we get to maybe 50 terms, we're getting an error that might be down to 1,000th, and now it's gotten so small that really at our resolution we can't see. But if you look on the left there with some of the computation that Desmos is doing, that R value is the error. So right now we're at about 13 thousandths for our error, and we're at the 70th partial sum. So pretty good. Depending on what you need, 70 terms is not a lot. I mean, a machine could add that up in a blink of an eye. What we can do is we can use this truncation error theorem actually in reverse. We could ask the question of how many terms do you need to add up to get the error that you like. And that would be just a matter of solving for n in our truncation error theorem. So we'll do an example of that next time. But yeah, it's converging quite quickly. So yeah, next we'll look at how many terms would we have to add up for this series, for example, to get an error of, say, 10 to the negative 8. So we'll look at that next.